Hi everyone, and thanks for the slot and the dedicated slot for me and the invitation also. And it's a great opportunity for me to talk about dependent types. And we're going to go through Scala 3 first, and then after we are going through the theory and the practice and to see the choice which had been done by Scala 3 and the choice which has been done by other languages and see some differences. So just a self-promotion, I work and I live near Toulouse in southwest of France, and I work with a company which is named Akawan. So we breed two products. The first one, which is of course of the hype, AA dedicated to DLP, with preventing data leak. So in order to increase the security around the data, which are shared with ChatGPT and so on, as you know. And then after also, we also provide another product, which is named Captain Go. We are French, so Captain Go, and which is a secure distributed system based on a peer-to-peer system based on actor paradigm, dedicated to decentralized execution with streamlined communication. So if you need information you are interested by, you have the links, and you're welcome if you want to ask some question. Now back to the presentation. First, we are going to go through Scala 3 and see how type dependency has been tackled by the language during the DOTI design at the beginning, 4 years before, if I remember. So once Scala 3 has been announced, and it had been designed with 4 new construction. And the first one, which is type lambda, which is the capability to define type constructor anonymously. The second one, which is the polymorphic function type. So we're going to illustrate this different construction. Even if you read a word of Scala 3, this is important for me because I'm going to use this example to do some comparison with another approach. So the polymorphic function type, of course, the match type, which provide but a computation capability in the type system, so which is done during the compilation. So we have execution done to compilation, which is a major issue. And finally, the introduction of the so-called dependent functional type. And so we're going to focus on this point mainly. So first of all, we are going to deep dive in Scala 3. And here we are going just to give a simple example in order to illustrate the two first construction which has been just listed before, which are the typed lambda and polymorphic function time. So first, in Scala 2, when you have to write, for example, the type of function identity, the type of the identity, function identity, we can write this with the square with the x and the x and the factorial x, or x to x. And this is, in fact, the usual way to design your type. Then with the type lambda, you can give another formulation thanks to this curious operator, which is equal sub. I don't know how to name it. So here we can see that we split the definition with the naming and the name of the type and its definition. Okay, and this type lambda, in fact, it's type constructor. It's just explain and expose what type constructor is in the language. So we already know that Scala offered, but here the type, highlights the fact we have a type constructor. We already have also generic function, of course, for example, a combine. So I don't give the implementation of combine, so it's generic also, but this is just for the example. We don't have to concentrate on to focus on the implementation. This is not the important part. But this combine can be also rewritten thanks to the polymorphic function type with the right now with the square also operation and the factorial. So if we do a first, and this is also called big lambda in order to do the comparison with the lambda and the big lambda in order to capture type, lambda to capture expression. to capture expression thanks to a variable. And here we have first, we can see we have two expressions. The first one, which is dedicated to calculator thanks to this operator. And here we have a pure functional polymorphic type, sorry. And since we can use it also, so we can define incrementation, so inc function, which is a function from type to type, because of the application, the type application of combine. So we apply the combine to the type int, thanks to the square, and then after we apply the result to 1 to the integer 1. And then after the type of this expression is of course the int to int. But since we have also some type constructor, this can be also replaced by identity type, the type identity of int, of course. So this is not, there's no magic here. This is the pure Scala 3. And here we just illustrate type lambda and polymorphic function type, quite simple. The second example here, we are going to use and illustrate the match type and dependent functional type. First, the match type is give us the capability to compute over the type. So for example, I define a type which is named case, which is waiting for a generic type called B, which is a subtype of Boolean. And the result of the type case is itself a subtype of string or int, okay? And then we have two very different cases. If my Boolean B is true, we return string, and if it's false, we return int. Okay, this is just it's not really useful, but just to illustrate the match type. Here we have to carefully to take care about what is true and what is false here. I mentioned that B is true, but B is type. So it means that true is a type also. So here we have to really take care about what we're reading here. Here, true is the type true, which is the subtype of Boolean. In other word, true is the Boolean reduced to the expression which is true. It could be seen as a reference type, but which is not. It is not a reference type. So here we have to take care, but we have the same with 1, 2, and the string and so on. So we have a kind of, I don't would like to say a trick, but it's a synthetic trick which is used in order to mimic the fact that we can use expression in type, but it's not expression, it's really type. Okay, so we are stay in the type world, and we don't have expression which are embedded here. Okay, we stay in the type level. But of course, we have capability to reduce. And we can define also a function, which is a default. And based on the default and the Boolean, we are going to return a case, which in fact, which is going to be specialized with the type of the Boolean, which has been the parameter. So here we see the dependency functional type. The result of the function depends on the value B, and we can therefore extract its type thanks to the dot type operator. And therefore the type operator give us true or false, the true or false type, of course. And then after, if B is true, the expression true, we return the empty string, and if it's false, we return 0. And here true is the value, the expression true, which inhabits the type true, and false is the value, which expression which inhabits the type false. And then after, we can easily call this, applying the default to the expression true, and we can say that the type of this expression is case of true, and if we apply the reduction thanks to the match case, then it's the string. Okay, and all this works fine in Scala, and we have to keep in mind that this operation offers a capability to have some reduction during the type checking stage, during the compilation. This is really important. So if you go back and keep in mind what's the Scala 3 and see how dependency are addressed in the Lagrange. So according to the Henk-Peter Barendrecht lambda cube, we have the first dependency, which is some terms can bind terms, okay? And this is purely functions. We have also terms we can bind types, which is in fact, this is the polymorphism. we have types, we can types. This is the type constructor. And finally, the much more complex is term types can bind terms. So this is a dependent function, functional dependent type. So of course, the first one is equipped in Scala 3. It's okay. In for the lambda 2, for the polymorphic function, of course, in Scala 3, it's available. The types can the types, of course, the type constructor as shown in the previous example, it's provided and available in Scala 3. And types can bind terms, it's a little bit more complex. Frankly speaking, we can say we have functional dependent types, but we are going to see that we can have some variation. So we can say that we have this feature, but it could be as a subset of all the capabilities we can tackle, we can address when the types can bind the terms. So first, saying this, we are going to rewind the story and restart from the basic. And to do this, the way I do it is that just to study some paper, read paper, and do my own language. So this is the do-it-yourself approach. So here, this is what we're going to do, just to step by step redo a minimal language in order to see what dependent type means and the difference of major language which are identified as the dependent type language from the other one. So first of all, we are going just to design the first language, which is called lambda 1. This is not important. We have two sets with sets of variables, a set of identifiers. We have two language of expression, language for the type. In expression, we have the first expression, which is the abstraction with the fat arrow. So I use the same syntax as the Scala 3, which has been chosen for Scala 3 in order to just to have to link the code and to have a pure comparison in order to increase the comparison. We have the application, of course, and some variables. And the other end, we have the types with basic types of integers and so on, all literals. And we have the function type with the arrow. So when we have a language, we have to define the type checker. I already mentioned the type checker do a lot of work behind the hood for you. And here we have to learn the basic of type checker, so the formalism which is behind, in order to understand what does it mean dependency when we talk about type dependency. So first we introduce gamma, which is this is really, it came from the academic paper. So sorry if it's mind blowing for some of you, but it's important. So first we have gamma, which is the types, the bindings. So we have the variables and the types, corresponding types. So the set of binding, or what we call hypothesis. We have a triplet with gamma, set of hypotheses, A, which is a term, and T, which is a type. And this triplet should be written like this: given gamma, the term A inhabits type T, okay? And then after, a rule is just a set of premises and a conclusion. And premises are triplets, and the conclusion are also a triplet, okay? And this rule can be read like this: when premises from P0 to Pn are verified, then we can conclude C, okay? So based on this basic formalism, which has been introduced, of course, we can read no, I don't have enough time, sorry. So back to the function, a lambda expression and application, we are going to just to mimic the type checker, how it works. So if we have the expression, and this should be quite easier because you already know functional type and so functional programming. So if we have function from X to B, what is the type from X to B? It should be a type. So it should be a type from M to N. And M should be linked to the variable X. So as a hypothesis, X should be of type M. And then after, we have to verify that B is of type N. Okay, this is what we call the arrow introduction. And we have the other one, which is which explain how the application should be typed. We have F applied to E if of type N, if F is a given type, have a given type which is an expression from M to N, and E should be of type of M. Okay, so this explains how the type checker works and how the code is verified. This is quite really simple. So here we just see a pure and a simple lambda calculus. So we can first try to introduce new construction, which if you follow the lambda cube, this is what it is done. So first we can introduce dependent functional type. What does it mean? We introduce the universal quantification, if you want. Or here we have a function which take a type, and we can address here x can appear on the right side. Okay. Of course, since we have dependent functional type, the functional type, which is the basic one, is just, in fact, a syntactic sugar, which can be replaced by its expression, because here the x does not appear on the right side, so we can do an elision and don't express the fact that we have a variable. And here we are with the crossroads. We have two approaches. This is the approach of Scala 3. First, we stay with two different languages, and we extend on the left side expression, and on the right side, we extend the types. And we can choose another way, which is we separate and we remove the boundary between expression and types. Okay, and therefore we have to define finally a types in order to define the type of type. It's horrible. Then after, so you go back to the type level, and if we do some transformation, the functional type, which is syntax sugar, can be expressed thanks to the dependent type. And then after, we have to express what is this variable. And if we go back to the literature in the academic paper, the variable x and r should be the same. And here we split in this rule, we build a bridge between the term and the types thanks to this variable. The same for the expression of the application, but here we have to recap the story. Here, E has been applied, F should be applied to E, and X should capture E when it's applied. So this should be expressed in the type. And here, the type expression here. Here, we just, in fact, recap that we have a story between the premises and the conclusion, and the fact that X should be replaced by E, okay? And here we show that we can show that the A is injected directly in N. It looks like it's a beta reduction in that. And finally, we have the type, which expresses the type itself. So the type dependent function is the type. So saying this, we can do first transformation, which is the dependent functional type. And we're going to transform this with our first language. So first, the type language can be defined by the type, IDT, and here the type constructor is expressed thanks to a function. So we don't do the difference between a basic function, which is the big lambda, and the small lambda. It's just a pure lambda, but this lambda takes a type in order to produce another one. Okay, the combine is the same. It's a dependent function which takes a type and produce and was waiting for an x, another x, in order to produce an x. We don't give the implementation. And then after the combine, the incrementation is just the application of IDT on integer and the combine of int and one, and here we retrieve the same expression than we have on the Scala 3. And of course, the reduction of IDT applied to int is into int, and this is done thanks to the reduction which I express in the type checker. Okay, this is important. I don't have enough time to the same type, but the same time we have the left injection, the right injection. So the same types, it's in fact the most important is some types can be the terms which are either a given types or another one. I use the either in order to keep in mind the either which is defined also in functional type. We have a choice. Okay, so I have the left of the right. Here we have the same construction. First we have the sum type with the plus in order to just to recap and to explain what sum type is with the left part and the right part. And we have expression in order to have the left injection, and the right injection. And finally, we have a third construction, which is the catamorphism, in order to explain the projection thanks to the left or the right injection. So we are going to see just a small example. thanks to this language, we can design the Boolean. So Boolean is a type. So here we design the type, the fact that Boolean is a type. Okay. A Boolean is defined like this. It's a unit plus unit. We have the left unit and the right unit. It's not a union, it's really a sum type. We have the left one and the right one. And we can define true as a Boolean with a left injection of unit and false, which is a Boolean, which is a right injection of unit. And then after we can define the AND operator, which takes two Booleans and return a new one. And this expression can be easily done thanks to a function. We take a left part and a right one. And then after we just apply the case on the left one. And if the case on the left one is a true, we execute the function here, which returned the right. So this is quite usually for the AND operator. And if the left part is false, return false. Okay. So I'm not going through the rule because it's really it's too long, but we have just most important in this rule here is once again, we recap the story and the relationship between the conclusion and premises, thanks to the dependency and the reduction. In fact, once you do the type checker, we try to increase and try to enrich the type in order to have much more capability to reduce the type in order to have the more precise type during the type checker. This is really important. And of course, the construction itself, it's a type. So back to our example in Scala 3, we have the case with the type match, and as you can see, the case is expressed only on the expression level. But since expression and types are merged, this can be easily reward using this small language, saying that case is a type from Boolean to type. Okay, and the expression is I'm waiting for X, a Boolean, and depending on the value of X, if X is a true, I'm returning a string, and X it's false, it's an int. But here the main difference is with Scala, X is the expression true, not the type true, the expression true. So here we see that the expression is directly used. We don't have to use something which is in fact which is called the path dependent type in Scala, which is we can use expression in order to extract types. Here we use directly the expression. And then after we can also reword the default using this small language here when the case type and so on. And here, once again, we have the same expression. So we have a real mirror between the type level and the expression level, between the default and the case. And we see that we have exactly the same patterns, but if the patterns return the type and this one returns the expression. And if you remember the type checking for the expression for the application and not more for the function, we say that the X from the left side and the right side should be the same. So if I decide to type this expression B, the B here should be the same as this one. So we are going to increase the capability to have a finer type when you are going to type check this expression. And finally, the default true can be explained with as a case true and the default apply to true. And that's it. So here we see that if we merge the two language, the syntax and the construction has been reduced. So it's the choice which is done by Scala 3, which is really it's really important because it's increased expressivity. Of course, it's had some deep impacts in the design of the language and the syntax and the capability. I'm not going to give a naive vector with size in Scala, but you can trust me, you can define it, but we have to define naturals at the type level. We can reuse the natural at the expression level. This is the price we have to pay with Scala 3. So during the expression, I do not cover product types thanks to dependent pair. I don't tackle the recursive types. It's 1 or 2 hours. And I don't talk about proportional equality. And this last topic is really important because we must know if we would like to use dependent language in order to have a better tool for engineering, for example, like Idris, in order to help you during the construction, the expression construction, or use proportional equality in order to have proof system, and so on. So you have different language with type system, pure dependent types where both languages are merged. I don't set up, I don't put here Scala free because this is not the case. We have Coq, for example, for the type for proof. Ada also with for the proof with Idris, Lin, F star, and Granule, and so on and so on. You have some references if you want to do deep dive in a type checker and dependent types, because it's a here I just scratched the surface. So it's a lot of work to read, and it's really how to say, it's a rabbit hole. So once you go in the rabbit hole, you're lost. So thank you so much, and sorry for my English, even if because it's really difficult to tackle the subject within 25 minutes. So I hope I open your some mind, or maybe don't.